So for this learning module, we're going to look at how to add vectors in 3 dimensions. And just like the 2-dimensional case, although there is a geometrical approach that we can take, we'll prefer to do the linear algebra approach, which involves decomposing vectors into their x, y, and z components, because it's much easier to handle when we're adding more than 2 vectors at a time. And that will be a case that we encounter very routinely in our mechanical analysis, where oftentimes the body will be acted upon by numerous forces. So the approach in 3D is the same as the approach in 2D. You take all the vectors that you're trying to add, you initially decompose them into your x, y, and z components. You take the collection of x components, add them together, collection of y components, add them together. Same thing for the z, collection of z components. And then once you have the sum of those individual component values, you simply use those to weight I hat, j hat, and k hat in order to express your resultant vector in rectangular form. So I like the way that this is written because it kind of emphasizes the key idea of why this is powerful. Namely, we're taking this resultant force, which is defined as a vector sum, and we're writing it as a bunch of scalar sums. If you notice, boldface here, so we have to follow the rules of vector addition in general, but these are just scalar values. So we've kind of did that simplification that we talked about in the prior lecture. So I wanted to do a couple different examples. This first example, we have a hook. It's being pulled in 2 directions by cables. We're told the magnitude of the forces that those cables are exerting on the hook, along with given enough geometrical information to be able to decompose these vectors into rectangular form. And what we want to do is find the resultant vector, which we can do after we do the decomposition. So I'm going to take and kind of scroll over here, and sorry about this. I wish I had a better setup where I could automate this part, but let me get all set up. So just to kind of motivate what we're doing, we want to find the resultant force as a vector, which by definition is going to be the sum of those 2 vector forces, F1 and F2. So we want to initially, in order to do addition as easy as possible, decompose both vectors into their x and y components. So F1, what do I know about it? Well, I'm given that its magnitude is 500 pounds. And another key to doing this problem is to be able to look and visually see that F1 as a vector exists only in the YZ plane. There is no component of that that's actually pulling away or out from this plane. And the book is trying to emphasize that to you by highlighting this triangle in a light blue type color. So we know that it's YZ plane only, which is going to tell us in advance that the x component of F1 should be 0. And in addition, we know that the geometry of kind of the decomposition of this force is similar to a geometrical triangle that's 3, 4, 5 along these specified axes, y and z. So as you probably can guess what's going to come, we're going to need the trigonometric ratios of this function alpha, of this angle alpha, I should say. We could actually get it by taking the inverse tangent of like 3/4, but that's going to result in some unnecessary math. All that we'll need in our decomposition is an expression for the cosine and sine of this angle. And just following our trigonometric rules, the cosine of this angle is adjacent divided by hypotenuse, or 4/5, that ratio of side lengths. And in a similar fashion, the sine, opposite over hypotenuse, is 3/5. So let's actually draw this force in the YZ plane and do the decomposition. So here we have F1, and what I want to do, and I know that its magnitude is 500 pounds, is decompose it. And I'm actually going to show the triangular addition here, and then I won't do that again, into a vector along the y-axis, and a vector along, and I should say positive y-axis, and a vector along the positive z-axis. And naturally, the y and z-axis are orthogonal, so this is a right triangle with interior angle alpha, where I know the trigonometric ratios from above. So again, I hope everyone is getting to the point where they can kind of see that cos alpha adjacent divided by hypotenuse is going to be the ratio of the y component of this force. And I'll add in little ones in here, F1y, F1z. So I know that F1y, cosine of alpha, is F1y divided by F1. So that means that F1y is just F1 times cos alpha, which is just going to be 500 times 4/5 or 400 pounds. And in a similar fashion, F1z is just going to be F1 sine alpha, which is just going to be 500 times 3/5, or 300 pounds. And notice I don't need any sign corrections there because, sorry, a little bit out of scope. Both components are pointing in the positive coordinate axes according to the system that we have drawn, which, just as a refresher, is right-handed, because if you take and align the base of your right hand on the x-axis and you curl in the natural direction towards the y-axis, notice that your thumb points in what they're calling the positive z-axis, which means that this is a right-handed coordinate system. I like to write, and you'll see I routinely do it, my vectors when I do the decomposition is kind of a triplet where I'm using these triangle brackets to show that it's a vector. This is my x, y, and z components, so it's just a more compact way to write it than actually showing the linear combination. So what about F2? What do we know about F2? Well, we know that its magnitude is 800 pounds. And what we're given, instead of unfortunately, it doesn't lie in a single plane, right? It kind of lies in a plane that's defined by the z-axis along with axis corresponding to the projection of this vector into the xy plane. So in order to describe the geometry of the line of action of this force, what they've told us is you can start on the positive x-axis, rotate towards the y-axis 30 degrees, and once you're there, decline by 45 degrees towards the negative z-axis. So following that same idea that I kind of did in the previous lecture, I'm going to start by decomposing this into a coordinate system that consists of the z-axis along with an axis that is aligned with the projection of this vector into the xy plane. So I'll call this the kind of xy axis. And I'm not going to worry too much about the sign of that because I'm going to take care of that when I go back and actually do the decomposition of this projection. But what information are we given? Where we're told that this vector, F2, which has a magnitude of 800 pounds, from the xy plane, it's declined by 45 degrees. So what that means is that I can, this of course would correspond to the z component of F2, and this would correspond to the projection of F2 into the xy plane. So in order to get that z component, this is a right triangle, of course, I need to take 800 and multiply by the sine of 45 because it is opposite of that angle. And also, I need to add in a negative value there. And this negative is due to kind of just I'm going to put in quotations, the geometry that we're given. So in order to be a right-handed coordinate system, the z-axis is pointing up. Notice that the z components of this vector would point down. And since we were given kind of a declination angle of 45 degrees, we're going to have to do that manual adjustment ourselves. In terms of composing F2 into the xy plane, that's going to be 800 times the cosine of 45 degrees. And then once I've decomposed into the xy plane, or projected into the xy plane, I should say, I'm going to need to do a decomposition. And what information are we given about the projection of this vector into the xy plane? Well, we know that its geometry is defined by a 30-degree rotation from plus x to or towards the y-axis. So I'm going to take from the positive x-axis and rotate by 30 degrees. So that's going to be my fxy, that quantity that I computed above. So it's going to have a y component, and it's going to have an x component. And if you notice, both of those, in terms of the geometry, if you close your triangle, are going to be aligned towards the positive directions, positive x and positive y. And we were told that this angle is 30 degrees. So what we can do is express, and this is, again, all F2, F2x. How would I get this? Well, I take whatever this side length is and multiply them by cosine of 30. So I'll actually show it here. fxy cos 30. But what is the fxy component of F2? So F2xy. You can kind of leave that out since the other vector we didn't have to do this projection. But it's going to be 800 cos 45. So again, I'm just substituting this in for my projection. And then that's all multiplied by the cos of 30. And in a similar fashion, in order to get the y component, notice that it is opposite the 30-degree angle. So just to show all the work, it's f2xy times sine of 30. And don't forget that f2xy is 800 cos 45 sine 30. So in terms of actually adding this together, it's going to be ugly, but that's okay. The x component of f2, and I won't actually do the addition to bore you on the video, is going to be 800 cos 45 cos 30. The y component is going to be 800 cos 45 sine 30. And the z component, way back up here, is going to be minus 800 sine of 45 degrees. And I'm sure I'm off camera, and I definitely am. Sorry about that. So what you need to do is take your expression for f1 and your expression for f2 and basically add the like components. So what will the x component of fr be? Well, take the x component of f1, which is 0, and take the x component of f2, which is 800 cos 45 cos 30. And again, you're going to be doing a lot of this in a calculator, so you won't have to show all this. But just do that same thing for the y and z, and you'll be in good shape. That's the kind of end of that example problem. So looking back at our notes and where we're at, let's take a look at a homework problem that you were assigned this week. It's due on Sunday. So we have kind of this fastener, and we have 3 forces acting upon it. And what's a little bit different about this problem, and let me kind of zoom in here, is you have geometry to decompose F1 and F2, but you don't have geometry to decompose F3 necessarily. However, you're given some information about the resultant force. Particularly, you're told that the direction of the resultant force is cos 30 j hat and sine 30 of k hat. And what that means is that this resultant force is going to live exclusively in the YZ plane. And the reason that I know that is it doesn't have an x component. The first thing we want to do in this problem is determine the magnitude of the resultant force. Now, I'm not going to solve this problem for you since it's a homework problem, but I wanted to get you set up because it's unlike any example that's in the book or any example that I actually have done so far. So let me get back to my ImageMate. So what you want to do here is kind of develop a linear system in order to solve for the unknowns that you don't have. So the first step that I would do is write FR in terms of your given info, kind of like what you know and what you don't know. So if you think about what you were told it's you were told a unit vector in the direction of FR. So remember, for any vector, we can always write it as its magnitude scaling a unit vector in that direction. So I can write the resultant force FR as, well, it won't have an I hat component, because if you notice, the unit vector that defines its direction doesn't have an I hat component. Its j hat component will be FR cos 30, and its k hat component will be FR times sine of 30. So that will be in units of pounds. Now, what you want to do is step 2. Basically write F1, F2, and F3 in rectangular form. So very similar to what I did above. And for F1 and F2, just do the same thing that we did for the last example. However, for F3, just define F3 as some unknown x component, some unknown y component, and some unknown z component. Now, it might seem that the final step here, let me actually say what that is. What you want to do is equate. Remember that the way this resultant force came about is by summing each of the individual components. So you're going to be able to get, and this is kind of a foreshadowing to what we're going to do in chapter 3, 3 equations here. And it might seem like you have too many unknowns, because you have the unknown components of F3 along with the unknown magnitude. But take some time to play with that, and I think you will figure out that because of the nature of the underlying linear system that you derive, you actually are able to come up with specific solutions for each of these unknowns. And you might notice something about whether or not those solutions are unique, and you can think about from a linear algebra perspective how that relates to both your number of equations and your number of unknowns. So I hope this was a beneficial video for you, a little bit longer than I typically like to go, 15:37, so I'm going to stop now.